thank you for the introduction. As you know, I am Asif Raihan, KHM Asif Raihan. So I was a PPI intern for Birla Carbon, which is in Ulysses, the southwest, like the most of city in Kansas. A little bit overview about the plant. So Birla Carbon is one of the largest producer and kind of supplier of carbon black all over the world. And they have actually 17 different facilities around the world in 12 different countries. In United States, they acquired, which are originally Colombian chemicals back in 2011, and then they have started their operation here. But originally, this plant was established in 1946, and its main purpose was to supply rubber, carbon black for tires that will be used for the Second World War, like that. So, and the main part why it was in Ulysses, because it was very one thing is it's very rich in natural gas. So the largest gas plant in US in the Northern America is in that it's a gas field. So that's the largest in full North America. And then also if you can so if you can see that it's right on top of this Ogallala aquifer that provide water for 7 different states. So the plant is right on top of that, and it owns quite a bit of land. So they have multiple water wells to extract water from the groundwater. Bad thing is there is no surface water, but you have a big source of groundwater. And this is the outlook of the plant. And the plant can make 12 different variants of rubber grade carbon black and 11 variants of industrial grade carbon black. Little bit about PPI approach we already know, but then this is source reduction and our P2 mantra. So I followed that, and I try to change the material, change the process, and change the technology to help the plant do better in sustainability practices. It's for change. So I really like the website of Birla Carbon, and they kind of envision the sustainability goals very strongly, and you can find they want to go full carbon neutral by 2050, and they have developed 5 different KPIs, sustainability KPIs for that, and those are they want to reduce the carbon dioxide emission by 22% by 2030. Similarly, achieve 80% in energy consumption efficiency by 2030. 50% of the reduction of the water withdrawal intensity, again by 2030. 75% of waste should be recycled, repurposed, and reused by 2030, and zero environmental release by 2030. So that's the KPI to track to achieve that goal. And according to 2023 report, the whole company is lagging behind on 3 of the 5 different KPIs. Additional to that, this Higo plant, the Ulysses plant, because there is no other source for water, what I found is like these water wells, the level is already depleting. So we have to reading for water wells. So this plant is considered a high risk plant for future water availability. So they have a very strong reason to, it's a strong incentive for changing to more sustainable practices. So that's why Birla Carbon and PPI work together, and I have worked with 5 different projects. First one was energy conservation with compressed air orange, then water conservation with by upgrading the current RO system, then water and energy conservation by steam condenser reuse, energy conservation with LED lighting upgradation, and then energy conservation by solar panel installation. So all of the 5 projects are done, and a good thing to know is like all of them are currently being implemented. Before diving in, I just want to give a very high level view, just simplistic process description. So this is a quite a bit of old plan, and it's now changed. So right now they have two reactors, reactor 2 and reactor 3, and their primary raw materials is heavy oil from oil refineries and coal tar from coal plants. And what they do actually in these reactors, see, so here they will atomize that heavy oil here. It will be, of course, first is heated by a steam, and then it gets atomized by atomizing air, and then you will burn it with a sufficient, only a sufficient air so that it can get partially burned. And with the partial burning process, you get carbon black. If it's fully combusted, then it will be carbon dioxide. You don't want that. You want carbon, the ash. Ash is carbon black. So that's why it's a partial burning process. And that air, that combustion air, is actually heated one. How does they heat the air? Is like they actually use the reaction tail gas temperature in a heat exchanger, and it gets heated from a counter flow mechanism. That atmospheric air from the blower will go, and it will come back in the inlet, mixed with that oil, atomized oil, and then it can get burned, then the combustion, and then also that air kind of gets separated by two different flow. One is tangential flow and one is axial flow. And that axial flow will take out the reaction product with all the other gases. Because it's heavy oil, there are impurities. So you will have hydrogen sulfide, you will have NO2, NOx, and SOx, carbon monoxide also. So those are called tail gas. So tail gas and your product, all of them will be carried out from the reaction zone by the axial air. And then it goes to the back filter. But before that, because it's still very hot, the temperature can go up to 2400 Fahrenheit. So you have lots of, one first is you have a quenching process for agglomeration, and then you have a cooling process here, where you again spray more and more water, atomized water, to cool down the temperature. So finally, when you end up to back filters, the temperature is 500 degrees Fahrenheit. In the back filter, what happens? You have series of back filters, and you have tail gas with the product. In the back filter, it's a filtration process. So you separate the product from the tail gas. The tail gas will come up from these lines, and the product will come down, and then it will go to a bearing process, and finally it will be dried. Then it will be go to the silos and for packaging. But on the other hand, the tail gas, that is actually highly combustible. So that's why it's a very recent installation process. It's like Birla now have two incinerators, and that two incinerators, what they do is like they take out that tail gas, and then now they burn that again with combustion air, and also they also use some natural gas, but mainly atmospheric air and little bit of combustion gas. If you just kind of, it's just a match. So if you just, because the tail gas is already combustible, if you just hit that, it will get combusted. And the heat is, so in the reactor, the temperature can go up to 2400, but in the incinerator, you can also get a heat of 1800 degrees Fahrenheit. So with that, what they do is actually, right now they have two incinerators. So one incinerator, that heat will be reused to produce steam. So that's called waste heat recovery. So they are actually kind of reusing that heat. But the other one, that is going up to stack, when by the stack. So right now they are kind of wasting a heat of 1800 degrees Fahrenheit. Many plants will kind of kill for for that heat, like spend much and much dollars, so many dollars just to get that much of heat. But right now they are kind of wasting that heat because they don't need that. They're just getting rid of that. But then the good thing is they are using the heat from one incinerator. That's better than nothing. So my first project was energy conservation with compressed air audit. Right now the plant has two different facilities. One called atomizing air facility, and another one is plant compressor facility or plant compressor room. So atomizing air is like, okay, so you are compressing air and then you are adding that to your fuel oil to atomize that. And the other one is plant compressor room. So you are using compressed air to pass the back filter for pneumatic gate control, for packaging, for bulk operation. So you need, so that's the utility. So all that air comes from the plant compressor room, and the other air, other compressed air for the atomization is coming from the atomic air unit. What I did, I used this same UV ultraprobe 9000 tester. So I was holding that gun with in my hand and then listening for leakage sound. And what I found is like, because this is kind of an old plan, there are some modifications still done, but then again, many of the lines are still very old. So from those, you have air regulators, you have air filters, you have air meters, pressure meters, some fittings. All of these have leakage points, and I was able to quantify, kind of hear for the noise, sound, the decibel reading, and with that recorded the air pressure. With that, I was able to quantify how much loss is there and how much, what is the quantity of in terms of cubic feet of air, also in terms of monetary loss. So I was able to get both of the values. What I found is like there are total 77 leakage points, and our project manager from plant, he will say there are more. And the thing was, I was not able to reach all of them. There are many. There are some of the lines were that high I couldn't reach there, or they were in a way where it's not safe to go there. But then I was able to find 77 major leakage points, and I found out it's like that only that identified leakage are accounting for 300 CFM. So you are making, so you are making around 2,500 CFM here, and you are losing 300 CFM by these leakage points. Maybe more. That's loss. That's actually costing you money. And then what I found out is like the annual loss for this leakage is $22,000 per year. And because you need just fittings, you need air meters. I work with the maintenance team to find the cost, the price, and then I kind of counted how many air filters you need, how many air meters you need, and added them together. But I did not add the labor cost here. But I did add a 20% cost, so to account for that. So there's this $6,000 maintenance cost is actually accounting for parts and 20% of the total cost. So I think that can kind of counteract a little bit of the labor cost. So what I'm saying is like, what I've said, my analysis said is like, if you try to maintain that, you can save annually $17,000 per year. The deductible will be very low, just 4 months or 5 months. But then to do that, to maintain that, you have to do 3 things. From the identified leakage points, immediately repair the bigger ones. But there will some of them will be lesser important. Okay, schedule maintenance. And because this is the old plan, you will always have air leakage. There will be always there. So that's why when I am calculating the savings, you see, it's not 20,000. I am only considering 80% of the total cost, total loss. So that's why it's 80%. So that's why you have to have a periodic audit. So my recommendation was doing all of them, and then it will cost you around $6,000 or maybe $7,000 per year. But then you can save all of that, and you can get back by on 4 months only. So that's the result from my first project. Then the project was water conservation with upgrading the current RO system. So because the plant make steam, and also this water is groundwater, so it is very high in hardness. So you have to filter it. You cannot use it just as is in a boiler. It will create plug up issue, blockage issue. And also they sometimes make premium grade carbon black. For that also you cannot use just the fresh water. You can't use that because fresh water has all those impurities. So that's why they are using a reverse osmosis system, which actually just filters through lots of membranes. You have multiple stages. But right now, this has a capacity of 110 gallon per minute. The recovery rate is close to 80%. So you are losing 20 gallon per minute as wastewater or concentrated water. And that water is being reserved in these RO ponds. Then they have 4 RO ponds, and then it gets evaporated from that area. But the issue is, by doing so, annually you are losing 500 billion like close to 600 billion gallons of water. And a common trend is like, okay, so we own the land, so water is almost free for us. It's not. Water is not free, and the layer is also already getting depleted. So we have to look for opportunities to reduce that reject rate for new technology. So there are 2 options. One was CCRO, closed circuit reverse osmosis, where you just recirculate the fresh water until you can, like right now is 91% based on the design, based on the water quality in the plant. So one proposal was 91% recovery rate, and another one I also contacted Pure Aqua. So they were saying, okay, we have 3 stages. This is old technology, RO work, but we have 3 stages, and that will give you 89% recovery rate. Another thing was this RO unit had a RO distribution pump. It's not updated. So this RO distribution pump was here. That was a constant speed mode. But then this RO system does not run so 24 hours. What happens is like I looked at the total data collection system C. It gives you the whole data for operation. It runs for only 13 hours a day. The rest of the 11 hours, this pump will run at full speed. So that's the total waste. So that's why that energy lost in this 11 hours is to 300 kilowatt hour, and the cost is $12,000. So what I proposed, I analyzed both of these options. But I found is like, because this is a 3-stage one, and it actually has less capacity, less recovery rate, and 3-stage one always needs more maintenance. So that's not really reliable. So I proposed the plan to go for a CRO unit, and the savings, the capital cost will be higher than the original traditional RO unit, but the annual savings will be more, and the final payback will be 4.7, and also you can save 3 million gallons of water consumption per year. And because if what I said is like, if you have a CCRO, you have to have the VFD feed with that, of course. Without VFD, you cannot do that. So that's why I also added that in the calculation. So if you have a VFD feed pump, a VFD distribution pump, you will be able to save 600,000 kilowatt hour per year. And that will correspond to 650 metric ton CO2 emission per year. And the good thing is it's already accepted, and right now they are working with the corporate office to finalize the plant design and everything. My third project was water and energy conservation by steam converted reuse. So again, the plant is making steam with the waste heat recovery system. And the idea is, okay, so we are using waste heat. So steam is free. Again, steam is not free because they are using reverse osmosis water, and you have fans and everything. So what I found is like the task was to kind of get the cost of the production of per hour. So per hour, the plant is making 18,000 pound per hour, and the cost is $18. So the plant is spending $18 per hour to make steam. And then what happened here? So just let me talk a little bit about this project because this is important. So from this boiler, the steam is coming to heat the water, heat the fuel oil, heat the delivery cones, and to heat unloading process. But after the steam is being used, it condense, it becomes water, and that water is RO water, pure water. But because the plant is quite old, the lines are not actually working as it should be. I have found total 7 different lifting stations that should bring up the condensate back to the boiler. The plant had 7, and none of them are working. And also, there were lots of steam traps. And I used this Ultra Pro 9000 again to check, and I found 21 of the steam traps are leaking. So that's why what the plant is doing. The plant is not using the condensate. And here, look at that. So per hour, you are making 18,000 pounds steam. And this 18,000 pounds steam will become 18,000 pounds of water, RO water. And all of that water is wasted like this. There are many points in the dumping station, dumping grounds, in the drains. All of the water is being wasted in the drain. So this was a very big concern for me. I spent 2 weeks on that. And finally, what I found is like in a steam, in that kind of old plant, I know like there will be some losses, there will be some leakages. So that's why I said, okay, you don't have to recover 100%, but you should recover at least 80%. So that's why I consider 80% water recovery. And with that, you can save 40 million gallons water per year. And if you consider current RO water system, that's have 110 million gallon per minute, so that is actually half of the production. So this 40 million is half of the yearly production of RO water. You can actually save half of that just by reusing this water. So that's why what I did, I kind of take all the maintenance cost, price, labor cost. It is coming about $20,000 per year or $20,000, but the savings that you can make because you don't have to pump that water again, you don't have to make that go through that whole process again. So that's the saving you can make is like $69,000 per year, almost $70,000 per year. So the payback period is like again 3 months or 4 months. But you can also save 14 million gallons water per year. And on the process, you can save 521,000 kilowatt hour per year. And that will again come back. You can reduce 593 metric tons of CO2 emission per year also by saving that water and saving that electricity. My fourth project was energy consumption with LED lighting application. So what I found, again, because it's the old plant, the plant was using lots of like high pressure sodium light, metal halides, fluorescent bulbs. So like all of us did, where I kind of counted the lights. I went in the night time also to see what light is working, which bulb is working, which bulb is not working. And I found there are some LEDs. Some of the good practices like in the plant, there are some rooms like the breaker rooms switchgear rooms that needs continuous 24-hour lighting. They have already changed that. They have already, the plant kind of was working towards sustainability. So they have already changed them to LED. So those lights are LED. But still in the public area, in the packer area, still they are using these old high wattage lights. What I found is that there are total 1,200 lamps that need to be changed. The current kilowatt consumption is 300,000 kilowatt hour per year. And because of these lights, the lamps, they are actually, even though the rated power is 175 watt, but actually they are not consuming ones. They are consuming more because they produce extra heat, waste heat. And I kind of did a fun analysis. It's like, okay, if the main argument in favor of metal halides is like the bulb cost is very less. Bulb cost for LED is like around $50, and the bulb cost for metal halide is $13. But if you consider a 1 year period, actually the cost for metal halide is more. It's $96 while your cost LED is cost you $63 only. Again, you have a more lights also. So this metal halide will go out in 1 year, maybe 1.5 years. But LED will last at least 10 years. And some of them will give a guarantee of 5 years also. So that's why I again tried to kind of build a model with, so there are some rules where you don't need 24-hour lightings, but because you have metal halides, with metal halides, you cannot put occupancy sensor because it takes 15 minutes to put turn on. And sometimes you only work for 15 minutes only. So you cannot wait 15 minutes to go to have a 15-minute work. So that's why, but if you change all of them to LED, now you can add occupancy sensor. So that's why I kind of designed a new LED the lighting system. Also, the number of lamps is now lessened, 1,150. Now we can add motion sensor. Now we can reduce the kilowatt hour consumption. The cost of the upgradation, so I took the price from our the electricity manager, process control manager. It doesn't include the labor cost. It just include fixture cost, lamp cost, and also some of the connection. The good thing was in all over the plan I found there were no magnetic glass. All of the ballast were electric. So that makes it easier to use retrofitted or like LED retrofitting. That was possible. So that's why the cost for upgradation is a little bit less, around $11,000. But then the saving you can make is $7,000 per year. So you can get back that investment by 1.5 years. On the other hand, it can save 64,000 kilowatt hour per year, 159 or 160 metric ton of CO2 emission per year. My last project was energy consumption with solar panel installation. The plant was mainly looking for the main office area. When I was there, I thought I found it like the water wells, 2 water wells, and the main office. All of them are in the same category of voltage. So why can I look for all of them? So that's why my initial I used PPI watts calculator again to kind of consider a bigger unit to cover all of the meters. But then later what I found, again, because of this water level depletion, the water wells, they are not sustainable. You have to redig. So you cannot design a portable or a specific unit only for the water wells because you don't know what will be your next water well will be there. So that's why again I toned it down, and then I said, okay, let's design for main office only because that's the stable one. And for the location, there were possible locations on the rooftop, but also because the plant owns lots of land, so there are lots of empty spaces in the front also. So I noted these areas, these three areas as a potential location. And then I contacted some of the companies. So the plant actually contacted their local supplier, electricity supplier, and I contacted King Solar, like brand name. So the King Solar was supplying solar panels in southwest Kansas, so that's why I chose them. And I was also able to arrange a site visit. So they came in the plant to look at the potential opportunities. And they have proposed, and yeah, they have actually, they also say to have a ground mounted unit will be best idea because that now we can expand in future. So what they finally propose is like right now for now a 54 kilowatt hour DC ground mounted unit, but in their quotation they also say it can be expanded to 1.2 million kilowatt hour. Sorry, 1.2 megawatt, 1.2 megawatt DC ground mounted because they have the land. And even though it's not solar powered, but it can be added to the main meter and it can offset the traditional power energy. So, and this King Solar, they have also, like I said, yeah, they considered a parent cascade saving 30%, and also they have considered that accelerated depreciation saving. And they said, okay, yeah, we know you will get that. With that, they were able to, we know like solar panels are highly costly, but with those savings, it still is more, but then the payback period is 8.5 years. The plant also conducted Fire Electric, that's their local supplier of electricity, but they didn't consider the federal tax credit. And also their average cost was much higher than like the data that I got from Energy Department database. And that's why that payback period was 60 years. So finally, my recommendation was talk to work with King Solar and corporate office to because the payback period is kind of higher, so that's why it was unsure will it be accepted or not. But because the plan, the overall Birla Carbon is they have a very strong sustainability goals. When I was leaving, I got information from the general manager. Is like that is also got accepted. So they are going forward for a ground-mounted solar panel for the main office, maybe by next year. So the saving from that will be 91,000 kilowatt hour per year, and it will be able to save 88 metric ton of CO2 emission per year also. So overall, in total, this is the summary is like the annual saving will be from all these 5 projects, the annual saving will be $193,000 per year. And all of them now are in progress for implementation. On the side, what you can see is like you can save 2,000 metric ton of CO2 by all of these projects. You can also save more than like close to 2 million kilowatt hour consumption annually, and you can save 17 million gallons of water per year. So, and now all of them are in progress. So that was a nice thing that when I got the update, just leave with the job when I was leaving, it makes me okay, now all of them are accepted. So that gave me a very good feeling. So this is my gratitude piece. I want to thank you everyone here, everybody and supported me in the whole process, my technical mentors, coordinator, my on-site supervisors, my colleagues. They drove 5 hours just to see this to give me more confidence, more courage. Thank you for all of you for the support and care. I really enjoyed this experience and I learned a lot. Thank you.
Thank you.
Questions?
Questions from the audience?
You went into some detail about the waste heat for the incinerator system. Are there any other areas of the carbon black process where maybe there was waste heat, but it was maybe a less significant like temperature difference or something, and so you didn't really.
So there were like multiple potential sectors. It's like because it's very high heat, the temperature is 2,400. There were, even though they have reflectors, there were like radiation losses over there. If you go near the reactor, you can feel the heat. So heat is lost. It is actually being lost there. So, but then because it's so high, and if you want to catch all of that heat, the cost will be maybe not that worth it. So that's one. And one other thing that I found is like that waste heat from the stack, it can be reused for the dryer process. But then there is the EPA regulation is like that if your dryer is in an enclosed area, the tail gas is toxic, so you cannot bring it in. So that's why they have no other way to just make it go out like as a exhaust as a waste. One thing they were considering like maybe using it for an organics ranking cycle, but again that yield is only 10%. So the saving and the investment, I didn't actually look into it, but what I got some impression from other maintenance people is like maybe it will not be that old thing. So that's why they are considering it back from 3 years. Still, it's not. There is no progress on that.
What was your favorite project?
Hard project. Steam condensation reuse, because the regular idea was okay, steam is free. So, but then I was able to kind of make them see like how much is how much you are losing, and then still there was a kind of and the confusion is like maybe something is going on, maybe still we are using some condensate, but I was telling I was able to show them it's like nothing is in there are pipes, there are lines, but nothing is there. So that was a kind of great revelation, and then that was fun to do.
Does the reject water from the RO system go out to the pump, to that water pump?
So there are 4 different ponds, and then what you do is like when one is full, now you shift to other one and let that one evaporate by. They have 2 evaporators, so you can have a forced evaporation or a natural evaporation like that.
Are there any other kinds of potential productive uses for that reject water, other than putting it in a pond for some kind of like thermodynamics?
This reject water is so high in calcium content and all the mineral contents. I have seen all those ponds. All those ponds has white deposits, and there is no living creature. You can see some birds flying over there, but you cannot see anything there. So that is so high in hardness. So you just have to wait for evaporate.
And there's some of the I've heard joke that using sludge off those ponds as a beauty.
Beauty products, yeah.
It's a mud. It just has a lot of that mineral content to it. So
Wow.
there might be a market there.
Might be.
Yeah.
Project for another intern.